Should we get going?
Yeah.
Okay, so good evening, good morning, good afternoon, everyone. Pleasure to have you with us. We are very happy to have Indranil Banik with us again to give today's OSMU lecture. Indranil is currently at the Institute of Cosmology and Gravitation at the University of Portsmouth. He obtained his master's from the University of Cambridge in 2014 and his PhD from the University of St. Andrews in 2018. Indranil was then a postdoctoral fellow at the University of Bonn and a research fellow in the School of Physics and Astronomy at the University of St. Andrews. Indranil has worked very extensively on MOND, Milgrom's modified Newtonian dynamics, and today he will talk to us on the tidal stability of dwarf galaxies as a critical challenge to cold dark matter. Over to you, Indranil.
Thanks. Yes, today I'm going to be talking about the tidal stability of dwarf galaxies in Newtonian and Milgromian dynamics. So the dwarf galaxies we analyzed in particular are those in the Fornax galaxy cluster and the classical galactic satellites, so classical satellites of the Milky Way galaxy. Yes, this is work that's largely been spearheaded and led by Elena Asencio, who's a PhD student in Bonn, and much of this was done during my own time in Bonn. But I'd like to also mention the crucial role played by the observers on our team, Stefan Misk and Aku Venhola, and of course the overall guidance provided by Pavel. Let me get to the importance of dwarf galaxies more generally. The idea in the standard lambda cold dark matter paradigm is that dwarf galaxies formed very early in the universe. Actually, they formed even earlier than galaxies like our own, which are thought to have formed essentially from the merger of smaller dwarf galaxies. So you get these this kind of picture in lambda CDM. These are, I'm sure, dark matter, but the idea is that they would also accrete gas, and many of them would become visible dwarfs. But you do also get dwarf galaxies forming tidally in lambda CDM. So that's when two galaxies interact and they draw out like a tidal tail. So of course, with spiral galaxies, by the way, because they need to be like gas rich and they need to be what's known as dynamically cold. So you need to have ordered material in a rotating disk, leads to a nice dense tidal tail, which then undergoes gravitational collapse into tidal dwarfs, possibly. So this does occur in the simulations, but since they're free of dark matter, they're very fragile and quite rare. What I wanted to mention before I get on to the Fornax cluster and the Milky Way is that dwarf galaxies are supposed to be, or dwarf satellites are supposed to be distributed sort of isotropically in this scenario, whereas in this scenario they would be very anisotropic. You also have like different types of dwarfs. You have late type, early type, more spheroidal dwarfs. An important thing is that dwarfs have quite a low stellar mass, but they have a high internal velocity dispersion, which exceeds the expectation from applying Newtonian dynamics to their visible mass. That is conventionally understood as being due to the dark matter halo, which makes sense if they were primordial. It doesn't make sense if they were tidal dwarfs. So that's just something to bear in mind. But in this project, we're not going to be using the internal velocity dispersion measurements, which you might be relieved about because these are very difficult to measure. So before I get to the main part of the talk, just one thing I wanted to mention is that the satellites of the Milky Way are distributed largely in a thin plane, which is unusual in the lambda CDM paradigm. It's not supposed to be like that. The same is also apparent around Andromeda. About half its satellites are in a thin plane, co-rotating dwarfs. Recently, we've got proper motions for some of them. clarifying that they are indeed orbiting within the plane mostly. Well, we only have proper motions for some of them. In the Milky Way, we have proper motions for all of them, and they are clearly orbiting within the plane. You also see something similar on Centaurus A. We can't really see very much further out at the moment. It's hard to know the 3D distribution of satellites, but there is strong evidence for similar kind of plane around NGC New Galaxy Catalog 253. So the point that these dwarf satellites are distributed in a plane, not spheroidally, suggests that they have a tidal origin, but the high internal velocity dispersion implies that they, well, conventionally it implies they have dark matter, which isn't possible if they have a tidal origin. So you have a contradiction here. And one way to get around this is to, if you could find some way to have high internal velocity dispersion without dark matter. So we'll get on to that. One way to do that, of course, is to use Milgromian dynamics of MOND. The main idea here is that galaxies don't need cold dark matter halos. After all, like, you don't normally invent large amounts of invisible mass in other areas of science. So it's a good idea to not do that, to try and understand the dynamics using only the visible mass. What happens then, you plot the acceleration. So this is a centripetal acceleration, v squared over r. You plot that against the Newtonian gravity from the baryons alone. Ideally, the data points would line up on the line of equality, but they don't. They follow like a track here. Interestingly, they follow a very narrow track. You can't see 153 individual tracks, even though I have got 153 galaxies here. So this is known as a radial acceleration relation, or RAR. So each individual galaxy contributes some points on here, but not all 2,700. The only way to get that, of course, by stacking the different galaxies. Interesting, if you were to plot like the rotation curve of 153 galaxies, you could actually see 153 different curves. They won't all sort of meld into one universal rotation curve. That kind of thing doesn't happen. But in the RAR diagram, it happens, and that's really very unusual. So what do we need to explain this? Well, obviously, you can't use Newtonian gravity, but because there is a one-to-one relation between the gravity that you have versus the gravity you expect in Newtonian gravity, you can apply a correction factor. And that correction factor comes in only at low accelerations. High accelerations, the correction should be smaller, or 1, if you like. So the important thing is, because the slope is half here on log-log axes, you need g to go as square root of gn a naught. In other words, gravity should follow 1 by r behavior, and that will lead to a flat rotation curve, because v squared by r, the centripetal acceleration, will match the 1 by r gravity when you're outside the bulk of the visible mass. So what I'm saying is the point mass gravity needs to scale as 1 by r at low accelerations. In general, you would simply have g equals nu, which is a function of gn over a naught times gn. But that's only for spherical systems. For non-spherical systems, you just put an extra, you just take the divergence of both sides. So this equation will capture pretty much all situations you might need to handle in MOND. All non-relativistic situations, that is. The A naught scale is determined empirically. The precise form of the transition is also determined empirically, including the fact that you need square root here rather than, I don't know, cube root or something. That's also empirical. An important consequence to understand here is that in this equation, nu takes as argument gn. That refers not only to the gn from your galaxy of interest, but also from anything outside that galaxy, any external gravitational source. So if you imagine a dwarf galaxy with a very low internal gn, then nu will be quite large. So the dwarf will, if you like, appear to have a large amount of dark matter. But if the galaxy is situated close to another large galaxy, like a parent galaxy, in case the dwarf is a satellite, then GN, the total GN would be large, because there would be contributions both from the dwarf and from the main galaxy. That would lead to nu essentially being saturated, or the gravity, nu would become close to 1. In that case, you would just get G equals Gn, and there would be no boost to gravity, even though the dwarf's internal Gn is very low compared to A naught. So in other words, the internal dynamics of an object can be affected by the presence of a uniform external field. In other words, if Einstein was sitting in an elevator which was freely falling in the Earth, the results of an experiment done there would be different to an elevator or a spacecraft sitting in deep space, far from any source of gravity. In other words, the strong equivalence principle is violated by this theory. So this is essentially the intermediate function, which this version works very well with the rotation curves of galaxies. So we'll use this one. So how do we test gravity using dwarf galaxies? Well, the key thing to understand, if you've got an isolated dwarf, the gravity, the internal gravity, called G dwarf here, is higher than in the baryonic Newtonian model. That's because of the new factor in MOND being greater than 1. So MOND has boosted the gravity. That's all very clear. We know that MOND works pretty well with the isolated dwarfs. So in ΛCDM, what people do is they add just the right amount of dark matter to mimic that. So in ΛCDM, of course, their explanation is that G dwarf is much higher than the baryonic Newtonian model because you've got dark matter. So that's all fine. Both theories give the same amount of dark matter, one of them naturally, one of them in an ad hoc manner. But if the dwarf were to get close to a main galaxy, then in MOND, the boost to GN would be limited because of the external field effect. In other words, the total GN would be a lot higher than in this case, because the total GN here would also come from the main galaxy. That would limit nu, and by suppressing nu, driving nu down close to 1, the boost to GN would be limited. In ΛCDM, however, there is no external field effect because general relativity applies. You've got a strong equivalence principle. The fact that the dwarf is freely falling in the external gravitational field of the parent galaxy has no impact whatsoever on its internal dynamics. So the internal gravity is completely unaffected by the fact that it happens to be close to a major galaxy. That's a consequence fundamentally of the equations of motion being linear and the equation of gravity being linear. In other words, the standard Poisson equation is linear in the density distribution. So in MOND, in this case, the dwarf has a lot less self-gravity. Therefore, it will be much more disturbed by tides from the parent galaxy. So if you've got the same tidal stress on the dwarf in ΛCDM and MOND, which you can assume because, for instance, we know the gravitational potential of the Milky Way reasonably well. That's an observational thing. It's not related to MOND or ΛCDM. But for the same level of tidal stress, the dwarf would be much more vulnerable to that tidal stress in MOND. So that's the key thing to understand, okay? Dwarfs are much more vulnerable in MOND because not only do they have the tidal stress, which is true in both theories, but they're also subject to the external field effect. This, by the way, leads to some pretty sensitive tests of MOND, as we'll see in a moment. So what we were doing in this project, so I will have some results in the classical galactic satellites later, but first of all, what we were looking at was the Fornax galaxy cluster, which is the second nearest galaxy cluster after Virgo, I think. It's about 20 megaparsec away, contains lots of dwarfs, some main galaxies, the catalog at 564 dwarfs, but only about 353 is suitable for our analysis. I'll explain why in a sec. So mostly they're either dwarf elliptical or dwarf spheroidal. We classified as the same. So this gives you some statistics for the observers in the audience. The dwarfs were classified manually as undisturbed, possibly disturbed, very disturbed, or you couldn't tell whether it's disturbed or not. For instance, the image didn't have enough resolution or something. So this will give you an idea what happened. So I think these are different color filters, I think, when they look at the same galaxy in each row, whereas different rows look at different galaxies. So in the first case, you've got something which is very disturbed, it's clearly elongated. That's very disturbed. This one's mildly disturbed. And this one's just a nice spherical blob, undisturbed. So that just shows you how the classifications work. We were looking we'd removed anything where the morphology is unclear because we needed the manual visual classification of the morphology. We took 2 and 3 together as just one category, that we have a simple scheme, binomial scheme, if you like, with 2 categories. It's either undisturbed or it's disturbed to at least some extent. We also removed any late type dwarfs because in the cluster, they should really have transitioned into early type by now. Late type dwarfs are probably line of sight contamination. We removed dwarfs with unclear morphology, as I said. We removed dwarfs too far from the cluster, so that's the aperture within which we're looking, leaving us with 353 dwarfs. This is the main slide with lots of equations, so it'll be fewer later on, I promise. So what are the main physical processes we need to worry about? First of all, the gas should have been removed already. This is something we argued carefully in our paper. But you can also see in some of the high mass dwarfs where you would be sensitive to the gas, that there isn't any left. So these are purely stellar objects. Well, unless they have dark matter, but certainly they don't have gas. You have harassment, which is disruption from interactions with the massive galaxies. So this is if a dwarf were to pass close to a massive elliptical in the cluster, there would be a tidal shock on the dwarf, which would heat it up, and over long time scales, this can cause the dwarf to disrupt as the cumulative effect of such encounters builds up. So we calculated the disruption time scale, and well, the formula needed to be applied very carefully in both theories, actually. So in ΛCDM, you need to account for the dark matter inside the dwarf, but also inside the elliptical. In MOND, well, the elliptical does have its gravity boosted somewhat by MOND, but the main effect is that the self-gravity of the dwarf is a lot stronger than it would be Newtonian gravity because of the MOND enhancement to the gravity. So this is described in more detail in our paper how exactly we did that. But suffice to say, disruption is not the major process that would be expected harassment is not the major process that we would be expecting to affect the dwarfs, okay? The main process which may cause some damage to the dwarfs is tidal disruption. So this is from the cluster's tidal field. What I'm saying is this is relatively much more important than this in both theories, okay? So, and there's lots of other papers which have suggested that, also in lower mass cases, like if you had Milky Way satellites, for example, dwarf galaxies orbiting the Milky Way and a few larger galaxies like the Large Magellanic Cloud. So you can imagine that a tiny dwarf galaxy orbiting the Milky Way is much more likely to be disrupted by tides from the Milky Way, which is just sort of omnipresent, versus like a chance encounter with the Large Magellanic Cloud, for example, which could happen, but it's going to be a rare process. And since we're doing a statistical analysis, basically harassment is not really a major issue. So in the rest of the talk, I'm mostly going to focus on the cluster tides. So this is just the overall gravitational field of the cluster. So in ΛCDM, you've got the standard equations, and the same in MOND, which I'm going to explain in a sec. So the main thing to understand is that this is a dwarf self-gravity in the Newtonian case. And this is the differential gravitational attraction towards the cluster center between the center of the dwarf and its edge. If the dwarf had a size of r tide. Now, what do I mean by r tide? What I mean by that is how big would the dwarf have to be given its matter content in order to be marginally stable against tides. So if you make the dwarf any bigger than that, it'll disrupt. But if it was smaller than that, it would be stable. Now, this is like a theoretical calculation because obviously the dwarf has a particular size. But you can imagine sort of growing it until the tidal radius, at which point it would disrupt. So this is a self-gravity and this is the tidal stress. The tidal stress multiplied by the size tells you the difference in gravity from the cluster across the dwarf. If that balances the self-gravity, that tells you the tidal radius. So you can tell that the tidal radius is going to have a nice cube root in the formula, which it does. In ΛCDM, importantly, you need to include the dark matter in the dwarf. Oh yeah, by the way, the cluster tidal stress is the same in both models because you can kind of see the cluster's gravitational field. So we know the cluster tidal stress. But that's the equation lambda CDM, where the dwarf's mass consists of baryons, and well, just the stars in this case, and dark matter. But only 4% of the total dark matter halo is assumed to lie within the optical half-light radius. That's important, but this is just a consequence of the shell theorem. We've tried some other assumptions regarding this, or tried things like checking in Illustris TNG50 how much of how much dark matter is there within the optical RH. But this is the important thing. Obviously, dark matter outside that radius isn't going to affect the tidal stability of the observed baryonic component because of the shell theorem. So in MOND, you have this, which is the equations look remarkably similar because for tidal stability problems, the dwarf's gravity is actually weaker than the gravity from the cluster. The reason is very simple. If the tides from the cluster are comparable to the dwarf self-gravity, then obviously the total gravity from the cluster is going to be a lot bigger than the dwarf self-gravity. And therefore, the total gravity is going to be dominated by the cluster. And therefore, you're in the so-called quasi-Newtonian regime, where the boost factor to the dwarf's effective G is always the same. So MOND becomes a linear theory, essentially, in the vicinity of the dwarf, with a renormalized Newton's gravitational constant. Well, this renormalization factor can be quite large, of course. So that's basically as much as I wanted to say. There's some important differences between tidal stability in lambda CDM and MOND, but as I explained here, if you just keep this picture in mind, as the dwarf gets closer, the EFE comes in MOND, but not in lambda CDM. That's basically the only real difference. Let me get to the tidal susceptibility from harassment, which is defined in this way. So a higher value of eta means more damage from harassment or from cluster tides. In the case of cluster tides, the larger the size relative to the tidal radius, the higher the eta. So eta is a measure of how disrupted or damaged by tides the dwarf should be. So in this case, the dwarf, this is the blue circle represents the actual size of the dwarf, and the red circle represents the tidal radius. So in this case, the dwarf is completely stable. In this case, the dwarf is less stable. We haven't drawn a case where the red ellipse is smaller than the dwarf because there shouldn't be such dwarfs. But this is just something to bear in mind. So basically, higher eta means more tidally susceptible. So these are the results for lambda CDM. The first row shows harassment, the second row shows cluster tides. So you can see cluster tides are way more important. That's why I'm going to talk only about cluster tides from now on. Importantly, in MOND, the effect of cluster tides is much larger than in lambda CDM. As I've just explained, that's not too surprising, but you can see here that the tidal susceptibilities are so low in lambda CDM that you'd expect the dwarfs are not really going to be affected by tides, whereas here they should be. So we're going to have a look at that in some more detail. So the first thing I wanted to share is 5 divided by the maximum size, R max, at which the dwarf would be detectable. So R max is the detection limit. So we know the surface brightness threshold of the survey. Based on that, given the stellar mass, there's a maximum size the dwarf could have to remain detectable. So in other words, nothing should be detected like much above 1 on the y-axis. The x-axis is just showing you the projected distance from the cluster center. The color coding is very important here. Blue undisturbed, red disturbed. So you can see that here, for example, there's only a few dwarfs to be classified as disturbed. They might just have had a chance to encounter with an elliptical recently, or it could just be like a misclassification, but they are disturbed, but it's not due to tides, for example. They just have an irregular morphology because there was more star formation on one side than the other or something. But as you get close to this red line, which we've marked on here, you can see the proportion of red dots is a lot higher here. Now, what we think is going on is that at low distances from the cluster center and at large sizes, or more precisely at low surface brightness, because remember, high y-axis means low surface brightness. So there's a lack of low surface brightness or diffuse dwarfs towards the cluster center. And just below this red line, which seems to be a natural edge in the data, the proportion of red versus blue dots, in other words, the proportion of disturbed dwarfs is a lot higher. So there's no dwarfs above the red line. Below it, there are dwarfs, but these are mostly disturbed. Even though in the population as a whole, disturbed dwarfs are not that common. So this is a strong evidence for tides being important in the Fornax cluster, which lots of other papers have argued as well. For instance, these dwarfs are a little bit larger here typically than further away, which those also attributed to expansion due to tides. But here we weren't looking at that. We're just looking at the visual classification that was done before we constructed this plot. So one thing to bear in mind, if I were to plot this in a more revealing way, I'm showing now the fraction of disturbed galaxies in each bin in the tidal susceptibility. So you can see here that the fraction goes up quickly. The error bars also go up. That's because there aren't any dwarfs in ΛCDM higher than this eta, basically. So you might think, oh, hang on, if a dwarf has higher eta, it should be more likely to be disturbed. But remember, these are very low eta values. At such low eta values, it's very unusual that the dwarfs would be disturbed. I mean, it doesn't make too much sense. But remember, these calculations are assuming ΛCDM. If I were to assume instead MOND, you would get these results instead. So this now looks much more reasonable because this is suggesting that maybe 10% of, maybe there's a 10% chance of a dwarf getting classified as disturbed, even if it's not really affected by tides. But that proportion, the likelihood of a dwarf being classified as disturbed then goes up as tides actually do start to come in. And that happens around eta of 1, which makes a lot more sense theoretically. But you might be wondering, well, hang on, how do you have any dwarfs where eta is 2.5? That's because we had to make do with projected quantities. So we need to do a more detailed model to assess what exactly is going on here. In particular, address two key questions. One is, what's the minimum eta value beyond which dwarfs start getting classified as perturbed? In other words, what's the minimum eta value above which you kind of notice damage to a dwarf? And what's the maximum eta value? The eta value beyond which a dwarf is destroyed. Because we've only got projected information, we need to sort of infer these quantities from a detailed statistical analysis of the problem, which I'm going to describe next. So this was, by the way, the first MCMC investigation I've done in my career. So I'm going to show you now what exactly happened with it. The first thing is to build a detailed forward model for the Fornax dwarfs population. For this, we construct a grid of orbits with different radii, different semi-major axes, and different eccentricities. So you can see here, these dwarfs orbits all have different semi-major axes, obviously. These dwarfs all have the same semi-major axis, but the eccentricity is different, and the focus is the same as well. So by trying a grid of different semi-major axes and different eccentricities, we get some kind of picture like this. What we do is record the maximum eta over the orbit, because we expect tidal disruption or tidal disturbance to respond to the maximum value of eta attained during the orbit. So for example, if eta rises above the disruption threshold somewhere in the orbit, the dwarf will get destroyed. We then consider the sky projected separation from all possible viewing directions to try and mimic how obviously the observations work. We only have projected information for a cluster 20 megaparsec away. So then we assign probabilities like this. So the number density of galaxies, of dwarfs in the Fornax cluster is assumed to behave like this. It's assumed to stay flat and then have some behavior like this. It doesn't actually have a sharp behavior as drawn here, but it's like some kind of curve with these asymptotic limits. So that's the number density. The density, the probability density per unit radius will have an extra factor of r squared because of the geometry of the universe being 3D. The probability distribution of the orbital eccentricity is assumed to have a simple linear dependence on the eccentricity. So with an average value of 1, obviously, and some slope, which is at most 2. Then importantly, the likelihood of a dwarf appearing as disturbed depends on the tidal susceptibility. There's some minimum floor, p-dist floor. There's some linear rise up to p-dist ceiling, which occurs at eta destruction. You can't get beyond eta destruction. If a dwarf crosses that, we mark it as destroyed and treat it as destroyed in the statistical analysis. So that's essentially a model. The floor arises because there's some baseline chance that even a dwarf that's completely unaffected by tides is classified as disturbed by the observers. The ceiling corresponds to like the opposite case, where even if a dwarf obviously is disturbed by tides, there's presumably some chance that observers don't notice that. For example, if it's very elongated, but observers are located along the elongation direction, then they still see it as circular on the sky and they classify it as undisturbed. That's why we expect p-disturbed ceiling to be a bit less than 1, p-disturbed floor to be a bit above 0. And we can try and quantify these things. We can quantify all these parameters in the statistical analysis. So this just shows you the same information, but in equations, in case that helps. So I'm not going to cover this, but if there's any questions, we can come back to this slide. Basically, the same information as the previous slide. So first thing we got out of this was the best fit model in ΛCDM and in MOND. Okay, so top row for ΛCDM, bottom row for MOND. The blue points show the observed values, the red points show the result in the simulation. So first of all, we managed to match the projected separation distribution pretty well. So the blue points just show the distribution of projected separations from the cluster center, which we've kind of matched okay-ish. I mean, our models are pretty smooth, whereas the observations have a bit of scatter. But anyway, we managed to match that. Now, the important things, what about the distribution of the eta value? Now, remember, the eta has to be calculated in quite different ways in ΛCDM and MOND. But you can see that the simulations give basically a kind of cutoff here, which observationally makes pretty decent sense, to be honest. So that worked. But you could argue the same thing in the MOND case. In the MOND case, it also works. It's just that the cutoff occurs at quite different eta. So notice the X scale is very different in these two cases. So the models work, but they work at different values of eta destruction, which is going to be very important. I'm going to come on to that later. Now here, if I show you the likelihood of a dwarf in each bin in eta obs being disturbed, we can work that out in the simulations. You can also work it out observationally. Again, we've got a decent match in both theories. There's a rising trend observationally, but there's also a rising trend in the simulations. This again works, but again, the P perturbed starts lifting off at much lower values of eta in the Newtonian case and in the MOND case. So that is really the main distinction. But otherwise, the quality of the fit is decent in both cases. So this shows you the main MCMC result. So that's the triangle plot, in case anyone wants to look at that. I'll just focus on a few important things. So first of all, the p-disturbed ceiling is greater than the p-disturbed floor at quite high confidence. This didn't need to be the case. Remember that the likelihood of a dwarf appearing as disturbed could, in theory, have a negative correlation with the eta value. So that's one important thing. So the flow versus p ceiling and the likelihood of going above the line of equality. Then the other key thing is the plot or the contours in the space of eta destruction against the minimum eta disturbance. So in ΛCDM, you're over here, and in MOND, you've got much wider allowed region. But importantly, the thing to understand, the eta destruction is very small in ΛCDM. In other words, it's saying in ΛCDM, it's saying that dwarfs need to be destroyed when eta, whenever eta greater than about 0.2-ish, which is not realistic at all. Whereas in MOND, it's saying dwarfs are destroyed whenever eta is greater than something like 2-ish, which makes sense. But we're going to come on to that in more detail later. The main thing is that it should have been order unity, the recovered value, which is the case in MOND, but not in ΛCDM. So what is a reasonable stability threshold? In ΛCDM, it's been argued that it's one. That's how we've set up the equations. We've used the standard formula for the tidal radius. In MOND, although I can't show this particular video, let me show you a different one, just to give you an idea. Let me show you a video of Crater 2 orbiting the Milky Way. I think this will work. Yeah. So here you are. This is Crater 2 orbiting the Milky Way. It first of all heads slightly away from so it started at the same major axis. It heads away slightly, and then it will start heading back in towards the perigalacticon. So now it's starting to head in towards the Milky Way. In all cases, the viewer is placed at the center of the Milky Way. So you can see that in this particular example, the dwarf gets very substantially distorted. So these are n-body simulations with the Phantom of Ramses code, which we also use for the Fornax Dwarfs project. I'll show some more detailed results from that in a sec. So yeah, that's essentially kind of what happens viewed from the galactic center. Fornax Dwarfs, of course, are not necessarily viewed the same direction as the center of the Fornax cluster, but yeah, so that was the Crater 2, and I'll just show you a different one, which is Amplia 2. And here it's similar. Again, it heads away from its starting radius, galactocentric radius. That gives it a bit more time to settle down. So it's still heading towards apogalacticon. Now it's crossed apogalacticon. It's heading towards perigalacticon, which it will get to, but that's only about 40 kiloparsec away, I think. So the title contains the information on how far it is from the Milky Way. So in this case, Amplia 2 has been pretty completely destroyed in this simulation. It's not going to get any better now that it's crossed perigalacticon, which in theory gives it a chance to recover whatever, well, to recover, but it's not going to be able to recover because it's been totally destroyed. So you can see here that this is totally destroyed. So we will this until the subsequent apogalacticon, which will be about now, I think. So yeah, that's just what I wanted to show here. So let me get back to my slides. So we simulated Fornax dwarfs at different orbital radii, but we're mainly going to focus on the 150 kiloparsec case with various eccentricities, various eta values. Eta values, by the way, refer to that at pericenter, which shows a certain mass and size. So what we did is we created graphs like this. The main thing is the size versus the size versus the time, basically. So what should happen if a dwarf is stable against tides, the size will oscillate in a stable or adiabatic manner. Adiabatic means it's reversible. The reason for the oscillation of the size is because the external field effect changes, and therefore the self-gravity of the dwarf changes. At pericenter, it's less tightly bound because of a weaker self-gravity due to the external field effect. That causes it to expand, as you can see with this orange curve, but then it becomes smaller at apocenter, and it sort of oscillates. That's what happens with the blue and orange curves. But with the green and red curves, the dwarf explodes. Okay, so it's not reversible, this behavior. It's not like cycles. The orange one is, but the red and green ones are not. So this panel shows you the distance. So like in the video, the dwarfs start to add the orbital same major axis. They head towards apocenter, and then they come back in towards pericenter, and they head back towards apocenter. I think they evolved for a short amount of time after apocenter. This shows you the aspect ratio of the dwarf. So using the shortest to longest axis of the inertia tensor, you can see that in the low eta cases, they are a little bit distorted still. That's because the external field effect causes the potential, even for point mass, to become slightly aspherical. But in the other cases, it becomes very elongated. And the velocity dispersion shows similar behavior again. It sort of oscillates in a nice manner in the low eta cases. In the high eta cases, the velocity dispersion shoots up. These very high velocity dispersions are not real equilibrium values. They're just what the velocity dispersion is of a totally destroyed and no longer gravitationally bound object. So using these simulations, the main result we got, we were able to quantify that the destruction threshold is about 1.5. Okay. So what does that look like compared to the results from our MCMC analysis? Well, that's what's shown here. The eta destruction 1.5 is nicely within the contours in MOND. So if you just look at the 1D probability distribution function of eta destruction, yeah, you've got 1.5 nicely within the inferred region. I think we actually argue in the paper it needs to be about 1.7 plus or minus 0.3 is our best estimate from the numerical simulations of the destruction threshold, which is very nicely consistent with the MCMC analysis of the Fornax Dwarfs. So I'm going to, before getting onto the galactic satellites, which I was asked specially to mention, just recap the conclusions for the Fornax Dwarfs project, which is that, which are as follows. So observations of dwarf galaxies in the Fornax cluster show us that some of them are disturbed. The main process that should be responsible for disturbance in general is cluster tides. We expect that therefore that the dwarfs go up to eta of about 1. Okay. Now the but that is an expectation. Obviously, you'd have to actually calculate R tidal in whatever theory you want, and perhaps in that theory, the maximum eta will be quite different to 1. If that's the case, sorry, but your theory is wrong. So this is essentially how the test we were doing works. In ΛCDM, that is indeed the case. The tidal radii are very largely disturbed, but observationally they are disturbed. And we've shown that this is not due to the detection limit, because the whole cluster was observed uniformly down to quite a low surface brightness. The MCMC analysis implies eta destruction is only about 0.25. In other words, dwarfs are destroyed whenever eta exceeds 0.25. If you are calculating eta in ΛCDM, that is. At that value of eta, the ratio of tidal force to internal gravity would be about eta cubed, which is obviously too little to destroy the dwarf. Therefore, the ΛCDM theory is ruled out. In MOND, the Fornax dwarfs are expected to be disturbed by tides, the main reason being the external field effect. No, I suppose a lack of cold dark matter, but this is essentially counteracted by the MOND gravity law. So the real difference is the external field effect. In this case, the required stability limit, according to the MCMC analysis, is as follows, about 1.9. the n-body simulations imply that we should found about 1.7 plus or minus about 0.3. So this worked. Now, in the last 10 minutes or so, I'm going to talk about the classical galactic satellites or Milky Way satellites, since I was asked to do so. So here, the project works a bit differently to the Fornax case. We've only got 11 classical galactic satellites, but we can only use 8 for this test. Sagittarius is going to be affected by the galactic disk, whereas we're treating the Milky Way as a point mass, and the LMC and SMC are interacting with each other, violating the assumption that tides from the Milky Way are the main process responsible, or the main source of tidal stress. On the other hand, although we've got very few objects, we've got full 6D phase space information. We know where they are, how far they are away from the Milky Way, not just in projection, but like the actual distance. And we know the proper motion, we know the radial velocity. So we have the 6D information. You also can get more detailed images, I suppose, because these are much closer to us. Yeah, these are all the classical satellites. We didn't look at the LMC and SMC and Sagittarius, but apart from these three, we looked at all the other ones. So let me just show you what they kind of look like. This is what they look like. Many of them show signs of tidal disturbance, actually. Not all of them, but many of them do. This has been sort of pointed out here. Well, not Leo2, but the others do. So let's try and understand this in lambda CDM and in MOND. So this shows you the eta value and its uncertainty in lambda CDM in orange, in MOND in blue. So the eta values are much higher in MOND in general. Let me go through the dwarfs individually now. So I'm happy to take questions on these individual dwarfs, but first, what I want to say, Fornax, it shouldn't really be much affected by tides, same in lambda CDM, but although these values are much lower than the destruction threshold of about 1.7 plus minus 0.3, I think the values are still high enough to be to have some disturbance. So when we looked at the Fornax dwarfs case, the minimum eta for disturbance was obviously much less than the eta required for destruction. I think you only need about 0.6-ish to create some observed disturbance. This doesn't really reach that. On the other hand, it looks pretty regular to me. Well, it's slightly squashed, but that might be due to the external field effect. Not entirely sure what the interpretation is of it being squashed in lambda CDM. But anyway, that's Fornax. So this is a Fornax dwarf spheroidal, not the Fornax cluster, by the way. This is Carina. In Carina, the eta in MOND is still pretty low, but it's high enough that some signs of disturbance might be expected. And I think you can see some signs of disturbance. The real thing in lambda CDM, it should really not have been affected by tides, by the way. So Draco in MOND, here you should definitely start to see some signs of disturbance. In lambda CDM, it absolutely should not. If you look at the real thing, it does look like it's being affected by tides, and it's pretty squashed. So that's Draco. Ursa Minor, eta MOND is quite high, quite close to the destruction threshold, actually. So you definitely expect some significant disturbance to Ursa Minor. Again, in lambda CDM, you're not expecting any kind of disturbance at all. Now, there's some morphological asymmetry. It's very squashed. So this looks like there is indeed some disturbance. It'd be nice if we did things like plot the axis ratio against the eta. We'll get on to doing things like that. Unlike the Fornax Dwarfs project, this hasn't been written up yet. So, but I was asked to show these preliminary results nonetheless. In Leo 1, the eta MOND is pretty small, but it's high enough that you might see some mild signs of disturbance, maybe. But observation, it looks like it's totally undisturbed. This is fine. In MOND, it's essentially what you're expecting. In lambda CDM, you're expecting the same, I suppose. So that doesn't necessarily distinguish between the theories. What I think is remarkable is that we've managed to finally get a very accurate eccentricity estimate and a very accurate very center estimate for Leo 1, which was historically very challenging. This is based on some special combination of Hubble Space Telescope and Gaia proper motions, a very long time baseline. So that's how we get such accurate results, even for the Leo 1 case. I think the same applies to Leo 2, though Leo 2 is a bit harder to do. I think Leo 2 is a bit, well, yeah, it's a bit less accurate for now. Nonetheless, what we can think, MOND, it shouldn't have been disturbed by tides. 0.27 is too low. In ΛCDM, it shouldn't have been disturbed by tides either. And observation, it hasn't been disturbed by tides, from what we can tell. So this looks all totally reasonable, to be honest. We've done things like write down crossing times estimates from Elena, in case you're interested in that. So that's basically as much as I wanted. Oh, sorry. Yeah, I forgot. There's a couple more that I need to get through. One which is a sculptor, where again eta is pretty low in MOND, but that seems reasonable here. It's only been squashed a little bit. Whereas in the sextant's case, there should definitely have been some disturbance, which certainly looks like the case if you just look at the image, or the isotopes. So that's as much as I wanted to say regarding the classical satellites. So this, well, here's the last slide. So I think I've stuck to time reasonably well. So what I wanted to say about the classical satellites is as follows. The classical Milky Way satellites are not compatible with ΛCDM because they lie in a thin plane and are co-rotating within that plane. So that's the number one thing. No, that's not the thing we were exploring. The thing we were exploring is that they also have signs of morphological disturbance, which is not to be expected given the very short crossing times. So, for example, the orbital crossing times are only order 10 megayear. So why would they look disturbed unless they have ongoing, unless there's an ongoing source of disturbance? And that would have to be the Milky Way tides, because there's nothing near these. The classical galactic tides, the galactic tides are far too weak to have any impact, however, in ΛCDM. That's because the dwarfs should be cocooned in protective halos of dark matter. In MOND, the properties are to be expected. So there's nothing unusual about this in MOND. Interestingly, in MOND, the phase-space correlation could have arisen because of a past flyby between the Milky Way and Andromeda galaxies, which could have created tidal tails between them, and these could later have settled down into a plane of satellites from the Milky Way and a similar plane around Andromeda. So I have a detailed paper showing how that would have worked with hydrodynamical MOND simulations. But that's not what I was mainly talking about today, of course. Just so you are aware, though, there are similar satellite planes elsewhere. Andromeda, of course, which might be related to the Milky Way, as I was saying, but also Centaurus A and MEC 253. So Marcel Paulowski has done a lot of work on these things, and Oliver Muller has done a lot of work on the Centaurus A satellite plane. But importantly, also, what I was saying about ΛCDM being falsified with the Milky Way satellites because of morphological disturbance, that is something you can also see in the Fornax cluster dwarfs. During the Fornax cluster dwarfs, the difference, just a sec, the difference is that we had many more dwarfs, which is good. But on the other hand, we had less information about each dwarf. So we had to do a careful statistical analysis to tease out the relevant information in the Fornax cluster. So just the final thought I'd like to leave you with is that observations of the nearby universe tell us that there is essentially no dark matter in galaxies, or certainly much, much less than expected in ΛCDM. And overall, the properties are better explained with a modified gravitational law. This is important to understand that these results, this conclusion is based on the nearby universe, where you can observe things in more detail So even if you have theories you work in a more distant universe, you might find a breakdown in the nearby universe. So there's just something to bear in mind, that we were looking very close to home in this project, especially in the second part with the classical galactic satellites, also in the first part in the Fornax cluster, which is very nearby. So that's everything I'd like to say. Happy to take any questions.
Great. Thank you very much, Indranil. Thank you for this very informative and insightful talk. Very topical. Please go ahead if you have questions. The talk is open for questions. Just use the raise hand feature, or just go ahead if you want to ask something.
Yeah, hello. Can you hear me? I'm Varun.
Yes,
Yeah.
Varun. Yeah.
Varun. Hello, Varun. Go ahead, please.
Yeah. So thank you for a very interesting and nice presentation, Indranil. So my question is, you see, you are comparing MOND to lambda CDM. Now, lambda CDM is not a single package. Like you see, about 20 years ago, you believed that, okay, CDM is CDM, right? And they're composed of WIMPs, heavy WIMPs like sterile neutrinos or gravitinos or something. But as you know, WIMP searches have not led to anything, right? With Lux and others. So now people are worried about the nature of the dark sector, not only dark energy, which was always worrisome, but also dark matter. And my question is, has anybody tried to do what you are doing with fuzzy dark matter? Because fuzzy dark matter is likely to be felt exactly in the neighborhood of smaller mass units such as dwarfs.
Yeah, that's a great question. We actually did do an extension sort of to our investigation of the Fornax cluster dwarf, where we found that if the dark matter content or the ratio of dark matter to baryons within the optical half-light radius is less than about 10, then you can just about explain the observations. So in a Newtonian gravity context, which is what I think you're asking, then you can plausibly explain the Fornax cluster dwarfs if you have a theory in which you can indeed, or in a theory in which you expect dwarfs to have such a small amount of dark matter. So this is not the case in cold dark matter. In cold dark matter, the expected ratio of dark matter to baryons is a lot higher than 10.
Yes.
But in fuzzy dark matter, if you're able to get it down to about 10, at the stellar masses we're looking at, which is about 10 to the 6.5 solar masses in the stars, then you could argue that perhaps that will actually explain the observations. I don't think anyone has done that calculation, but if they were able to do the calculation I mentioned, which is simply the ratio of dark matter to baryons within the optical RH, and get results below about 10, then I'd say it could work. But yeah, I don't think anyone has explored that.
Great. I'd be very interested. I think this is a very nice project to try to do this in fuzzy dark matter, because there are new pressure effects caused, by the quantum pressure.
No, I understand. In that case, yes, the dark matter becomes much more diffuse, or especially at the very centers of dwarfs, or indeed any galaxy. You don't get this. You can't get this cuspy behavior that you expect in CDM.
Yes, absolutely.
Right.
So if you do notice a paper on this, I would greatly appreciate it if you brought it to my notice at some time.
Yeah, we looked at that. I think there was one paper, one study looking at self-interacting dark matter for the case of the Anclea 2 and Crater 2, but that was trying to fine-tune the initial conditions. In the Fornax case, of course, what I was talking about with regards to the ratio of dark matter to baryons, that would need to be a more generic property of your simulation, because we were doing a statistical analysis of a large number of dwarfs. So it's not enough if you do a cosmological simulation with fuzzy dark matter, for example, and find one dwarf which has a low dark matter content. It would need to be in general that dwarfs should generally have quite little dark matter within the baryonic radius.
And also the simulations are going to be much more complex than just simple.
That's true. That's true. Actually, it's hard. It's only relatively recently become possible to get down to these kinds of masses in lambda CDM simulations, like in TNG 50.
Yes, that's right.
I think Pavel had a question.
Yeah, Pavel, go ahead, please. Thank you, Varun. Pavel, go ahead.
Yeah, on this fuzzy dark matter issue, it fails on the satellite galaxies of the Milky Way, right? Because the optical regions have very high mass to light ratios. So you can't say that the mass to light ratio of 10 is possible because we see hundreds, if not even thousands. So that is not a viable direction to go.
Oh, you mean for ultra-faint satellites?
Well, yeah, exactly. So you can't propose that the fuzzy dark matter is different in Fornax cluster than in the nearby the
In
Milky
ultra-faint
Way.
galactic satellites? No, of course not.
Yeah, exactly.
Yeah, that's actually a good point. If you were able to make fuzzy dark matter work in the Fornax cluster, then would the ultra-faint galactic satellites become tidally unstable then? I don't know.
You wouldn't have the high mass to light ratios.
Yeah, that's right. I mean, I have heard that in the self-interacting dark matter case, perhaps it's different because you can have this so-called core collapse occur. And in that case, you could have high mass to light ratios, but you can also have dwarfs which are prior to the collapse has occurred. And that would be more in line with like the results of the Fornax. But it's very contrived.
But self-interacting dark matter doesn't reduce the wavelength of the de Broglie wavelength, right?
No, self-interacting dark matter doesn't affect the de Broglie wavelength, no.
So that direction I don't think is viable at all. I mean, so fuzzy dark matter concepts will not help to remedy these issues.
Probably not once other constraints are imposed. Sure.
Yeah.
I mean, you know, the simulations are not simple because if you actually look at fuzzy dark matter, it's really a scalar field which is oscillating, and the amplitude of the scalar field gives you the density roughly, and it's different at different points in space. So you're looking at, you know, all kind of you're looking at shell crossing, their caustics take place there, right? And it's a very inhomogeneous scalar field, you know. So that way the CDM, lambda CDM is a very simple, you know, simulation to do just in the dark matter, forgetting about the baryons, right? But here the dark matter simulation itself has its own complexities. So unless one actually does it and sits down and thinks about these issues, both in the context of our Milky Way satellites and in the context of clusters like Fornax, it's a little difficult, at least for me, to understand, you know, whether some of these issues will be resolved or not. It's not a straightforward back of the envelope, or, you know, it's a very complex exercise, I think.
Yeah, but
it's two completely different ball games here: collisionless dark matter and fuzzy dark matter.
If the ultra-faint dwarfs, which are the size of tens of parsecs, have high mass to light ratios, then the de Broglie wavelength must be much shorter than 10 parsec, about. And then this argument breaks down because it starts to behave like cold dark matter, because a short wavelength of 10 parsec is not relevant anymore on kiloparsec scales, right? So fuzzy dark matter is not a viable option.
That's right. If you're, I think I understand what you're saying. That if fuzzy dark matter were to make a difference in the Fornax dwarfs, that's only possible if its de Broglie wavelength is greater than about a kiloparsec, and in that case, it would lead to some potentially very severe problems matching ultra-faint galactic satellites.
Yeah, you see that the de Broglie wavelength depends upon the mass and also the density, right? If you just look at it, you know, in a simple m squared phi squared plus lambda phi 4 theory, right? You know, so it's different from an m squared phi squared potential, and it's different for, you know, other hyperbolic or plateau potentials. So you really don't know what the potential you're using for dark matter is. Okay,
what are you saying that
paper on this, but at the linearized level,
how does
you know,
the de Broglie,
that's one thing. I please let me complete, right? Now the second thing, and this is quite important and very interesting, is that you see, if you look at the DAISY results, right? I mean, I'm not saying they're correct or they're wrong, right?
The DAISY results. You mean the baryon-acoustic oscillation?
Yes, exactly. You know, they're telling us something very strange is happening to dark energy, right? And there are papers now which are talking
It's a
about.
completely different issue.
No, I know. Let me complete my sentence, please.
Okay.
And they're talking about interactions in the dark sector.
Yeah.
Interactions between dark matter and dark energy, right? If dark matter and dark energy do interact, I'm not saying how, right? But if they do, then dark matter is a completely different object than lambda CDM, right?
I agree.
So you might have something completely new to play with. I'm not saying it's true or not. We have to wait till Euclid. We'll have to wait. But if there's an interaction in the dark sector, then it's going to be important for a whole host of problems. That's all I'm saying.
I suppose so.
But then
All right,
you're at a completely different cosmological theory and not lambda CDM anymore.
yeah,
right?
clearly that is not
Yes,
lambda
of
CDM.
course. Of course. So one shouldn't get hung up on lambda CDM. One shouldn't get hung up on lambda CDM because one assumes that, I mean, it has been, a very important focus of us for a long time. But if it is not lambda CDM, and if you're not allowed to treat the two dark sectors independently, then you're, so any problem that you are facing now, you have to remember that the WIMP theory of dark matter has gone out of the window, right? And we really don't know, even in the standard model, what dark matter is.
I agree.
All these lambda CDM simulations are going way back to the standard paradigm, which has been with us for 20, 30 years already, right? But I doubt the paradigm.
Can we take like the question from Janek now, maybe?
No, Indranil, let's just complete, then we'll go to Janek.
Okay, sorry.
Varun, just a quick question. So heavy sterile neutrinos are also ruled out, is it?
Yeah, I don't. I'm not sure about the sterile neutrinos, but all the other WIMPs,
Yes.
all these underground observatories like Lux and all, they're very strong.
But to my understanding, the sterile neutrino is probably still in the picture, close to the neutrino floor. So in that context, Pavel, I wanted to open up for all of you, Indranil and Varun, a little more general discussion.
Okay.
We do have difficulties with MOND and CMB anisotropies, assuming that the anisotropy is primordial. Can we consider a hybrid scenario in which dark matter is important in cosmology, but MOND is important on galactic and subgalactic scales? Where do you stand on that, Pavel? I want to know.
Yeah, that is definitely possible. I mean, this is the so-called neutrino hot dark matter or new HDM proposal, which has been discussed since about 2009. So what happens here, you replace the cold dark matter in lambda CDM with the same energy density in hot dark matter or sterile neutrinos with the rest energy of 11 eV, which causes galaxies to be unaffected. So MOND still works there, but it comes in galaxy clusters.
And CMB anisotropies.
Right, and it comes in for the CMB. The reason it comes in for the CMB is because at those high redshifts, MOND isn't very important. The gravitational fields are higher than A0, but the extra matter is important. So you've got it also comes in with...
So can, in such a scenario, can we make the dark matter subdominant in the middle galactic regions where the
yes, you can. Yes,
flat?
This has been shown that for galaxies are unaffected by these sterile neutrinos.
What is your stance on that, Varun? Varun, what's your stance on a hybrid model?
See, for me, both the gravity sector and the matter sector are wide open as of now, right? I'm just looking at new observations that can shed light where theory must go. But Indranil is right that there's the free streaming scale in neutrino models, right? And that's roughly 30 megaparsec divided by the mass of the particle, roughly. And so this standard HDM thing, right? Now the problem is that so it should work, yes, definitely. I mean, we have to test it out, but it'll be a hybrid model in a sense that you'll have dark matter. Now the thing that is also very important and has nothing to do with the seminar today, but which is very intriguing, is the discovery of very early and large galaxies by JWST, right? Which is also challenging lambda CDM in a certain way. And I'm wondering whether you need modified gravity for that, or you need something else to give us structure that early on, right? I don't know if MOND has the answer. I'm not an expert on MOND.
No, but it's good. It's good because I remember. I think who was it who actually predicted that MOND will have high redshift galaxies, precisely the kind that JWST discovered. Not Stacy. I'm forgetting. Maybe Paul
Sanders, I think.
remember. Huh?
Sanders.
Barry Sanders. Yeah.
I see. Okay,
Yeah.
that's interesting. Because I think that's a very important recent discovery, and very intriguing.
Pavel, where do you stand on the hybrid, dark matter plus MOND models? Dark matter good for cosmology, MOND good for galaxies.
We've been testing this new HDM model quite extensively, and it cannot form structures fast enough. But the problem there is using the CMB as the initial condition. So if one forces the fluctuations to be given by the Planck power spectrum, which are valid at a redshift of 1100, then this model forms structures too late. It does form massive clusters, but too late, far too late. And the work of Elena on El Gordo, for example, then already becomes a major problem for this model too.
I'm sorry. Are you talking about CHDM? Are you talking about CHDM or HDM plus MOND?
So new HDM
plus MOND.
Yeah. You're saying, Pavel, that HDM plus MOND will have problem with early structure formation. Is that right?
With early galaxies. Galaxies.
Yeah, that's what I mean. Early structure formation, early galaxies. Yes.
But MOND forms early galaxies, no?
Yeah. So why shouldn't HDM plus
MOND? MOND doesn't form early galaxies if you take into account the proper initial conditions.
Oh, really?
Yes.
Yeah, it doesn't. No, it's too smooth.
Oh, it can't do it. Okay.
But what about the
I thought Sanders said something like to that effect.
Yeah, but this is based on some very simplified calculations in 1998 using a completely incorrect cosmological model in which the universe is more than 20 billion years old. Those results should be completely discarded.
Oh, I see. Okay. So you're saying that in standard MOND cosmology, it's difficult to get.
You don't get galaxies until about redshift 4. However,
until redshift 4?
Yeah, because you don't have any.
Stacy's wrote otherwise, right?
Yeah, but it's not based on any detailed calculations of how MOND would actually work in a cosmological context.
So you don't agree with Stacy. You don't agree with Stacy.
No, because Stacy's calculations aren't based on any actual detailed calculations. If you don't have any power in the, if you don't have cold dark matter, you have negligible power on galaxy scales at early times, and therefore it takes much longer to form galaxies, even with MOND gravity. But the calculations you mentioned with Sanders assume essentially the same amount of power on galaxy scales as in lambda CDM, which is completely impossible in MOND, because the reason for having so much power on galaxy scales in lambda CDM is because of the CDM, which is obviously absent in MOND.
Then we are better off with dark matter on in early universe, right?
In the early, yes, but
it doesn't work. It doesn't work too. You cannot make the galaxies we observe at the redshift of 15. And
that is a problem
in particular, one cannot form elliptical galaxies, which are very ancient and very massive, right? So these ellipticals formed at the redshift beyond 15. That's what the stars tell us in these ellipticals. So neither lambda CDM nor this new HDM model can account for that. And so we have to get back to the critical question, what are the initial conditions?
Yeah, because if you had either you had lots of power on small scales initially, or you didn't.
No, that's correct. That is why people are, I'm sorry, that's why people are invoking primordial black holes now, right?
For example,
because you get seeds at very high redshifts will accrete matter, right?
Okay, that may help.
Maybe, but the situation is actually quite simple. So the situation is that the published power spectrum is only valid strictly for the lambda CDM model because it's been calculated with that being valid. Because you don't see the power spectrum, you have to calculate it from what you observe. True. And so a different cosmological model, like a new HDM model, would lead to a different power spectrum, but we don't know what that is because nobody's done the calculation which means that if we now were able to infer a power spectrum valid for the new HDM model, we might get early structure formation.
You mean if you had more power on small scales?
Exactly, and so this is what Nick Samaras, a PhD student in Bonn, he's finished his PhD now, but that's the direction he's looking at. So to try to infer a power spectrum at a redshift of 1100, assuming there was a hot Big Bang, valid for the new HDM model, and that will be different to the power spectrum which we today know, which is given by the Planck data.
No, wait a minute. Are you saying, sorry, Pavel, thank you. That was very interesting. Now, are you saying that the Planck assumes a very strong prior of lambda CDM when showing its results? That they are prior dependent, right? That's what you're saying.
Yeah, exactly. I'll be covering that on the 17th of October.
So that should be pretty, it's a very interesting exercise for somebody to actually do it. You've got the data and reinterpret the data using a different prior.
Yes.
Yeah, because you have different structure growth. So these effects, so the gravitational weak lensing, scattering of photons on electrons, and the potential wells, which change all the evolving potential wells, which change the energy of the photons. All of that is different in a different cosmological model, and so you have to recalculate the power spectrum from a different for a different model, and nobody's done that yet. So, and if we do that, then maybe we get initial conditions for the new HDM model, which can maybe form structures very rapidly, but we don't know.
Okay, so, thank you. That's very interesting.
Thank you. Also, we have one more complication, right? Like the cosmic dipole anomaly, the work by Subir Sarkar and group, which is now questioning the entire Friedman-Robertson-Walker paradigm on large scales. Would any of you kindly have a view on that? I'm quite concerned that that's a major issue. It's there's a paper they have now in Reviews of Modern Physics, I think Nathan Seacrest and all. Right. So, I mean, we can't ignore it.
Sorry, before you open that question, I do feel I have to point out Yannick Kozitsky has been waiting a very long time to ask a question.
Okay, we come back to this. Sorry to make you wait, Yannick. Please go ahead.
Thank you. Do you hear me?
Yes, we can hear you. We can hear you.
Very good. Thank you for a very nice presentation. It's very interesting. I would like to ask about the interpolating function. Why you choose this simple interpolating function Ni? It is not compatible with solar system according to analysis of ephemerides by Fienga and of Nesvorny.
Right. Yes, yes, but that's true. But in the let me go back to the interpolating function. So one thing I want to mention is that for galaxy scale problems, this interpolating function fits the data very well. It's true that at even higher accelerations, it doesn't converge fast enough to 1 in order to be compatible with solar system ephemeриdes. Actually, there aren't any MOND interpolating functions which can be written that are in agreement with the Cassini radio tracking data from Saturn simultaneously with the rotation curve constraints. But certainly if you were, what I would say is there have been some issues making MOND work on much smaller scales than galaxies. So if you assume that there's some problem with applying MOND to much smaller sub-parsec scales, and understand that in this project, we were only probing scales which are obviously much larger than 1 parsec, look at kiloparsec or kiloparsec scales at least, then for that kind of problem, the simple interpolating function does provide an excellent fit to the galaxy rotation curves. And therefore, it provides a reasonable approximation to how MOND would need to work in order to fit galaxies, and therefore serves as a reasonable basis for how to go about analyzing tidal stability.
So in short, you determined this simple interpolating function by analysis of the rotation curves of those galaxies?
Yes.
Okay, very nice, very nice. Thank you.
Thank you, Yannick. Thank you, Indranil. So maybe coming back to the cosmic dipole anomaly, my reading as a novice is that cosmology seems to be in doldrums. I mean,
with that result, there was this study which looked at the cosmic radio dipole in some detail. So what they did is they took some very deep pointings with the Meerkat radio telescope, 391 pointing.
Sorry, just in brief, Indranil, they disagree with Subir Sarkar et al., is it?
Yes, they find that the final results are consistent with the CMB dipole in terms of the direction and amplitude.
I see. So thanks. I didn't know this. Yes.
Yeah. Now, there are actually some plans to do some more detailed and statistical analyses to accounting for, I don't know, like relative calibration biases between different surveys and things like that. But in general, it's still unclear whether you would really have a significant, well, you have a radio dipole, as in the number counts do have a dipole, but it's still unclear whether that might be consistent with the CMB dipole.
Okay.
I just like to mention a thing, and I mean just a general thing.
Yeah.
Please go ahead. Please go ahead.
You know, for TP and Indranil, there's going to be a conference in Bangalore in December, which is going to focus exactly on cosmological tensions, and Subir is going to be there, and lots of other people. So if you feel like attending, I mean, just keep it in mind. It's going to be
Thanks for the update. Yes.
It's an RRI in December.
Bangalore, I see.
Yeah, it's focuses on cosmological tensions. So I guess all these things will start coming up, right? So
great, yeah,
very interesting. It's going to be interesting.
Yes.
So
thank you.
On the dipole front, since we're already on that issue, right? That's really a sort of, you already alluded to it, sort of a questioning of the FLRW, sort of the entire system that cosmology is built upon. But you needn't even go as far as this radio dipole. It's enough to just, so the way I see it is you can also picture it from the perspective of, in principle, homogeneity and isotropy, which is sort of more general, the cosmological underlying principle. So Indranil actually gave a talk here a few months ago on the KBC void. Like it's really our neighborhood, and one of the results that isn't yet published, but it's been submitted, is that actually, so for example, the apparent the Hubble parameter. So when you construct your supernova, your Hubble diagram to infer the expansion rate of the local cosmos, then so some recent work by Hu et al. They actually find that it has also a dipole structure, which happens to align with the bulk flow direction, which is a direct prediction or a direct consequence of the peculiar velocities, of the outward peculiar velocities that originate from this KBC void, right? So there's also a completely sort of, it's similar, it addresses the same issue of sort of isotropy and homogeneity of the universe, actually, if that is even
it's a much lower redshift, but yes, that's an important thing to bear in mind, that the claims that high redshift with the radio galaxies, the radio source counts being anisotropic, this refers to like redshift 1 and beyond. That's still very controversial. What's much less controversial is that there does seem to be some anisotropy in the local universe. For example, if you were to use galaxies as your tracers and compute the bulk flow, there is strong evidence for a bulk flow. Now, to some extent, you can have a bulk flow in lambda CDM, but the observed bulk flow is about quadruple the expectation. So there are strong hints for homogeneity and isotropy, or departures from homogeneity and isotropy in the local universe to a greater extent than is possible in lambda CDM. That certainly seems to be the case. Obviously, these things are not supposed to hold exactly in lambda CDM either. But regarding what you're saying,
suppose we leave lambda CDM aside, and just ask the generic question: is the universe homogeneous and isotropic beyond, let's say, 100 megaparsec scales?
So I mean, the study was trying to address this kind of issue, though it didn't, unfortunately, satisfy the last part of your question. We're going beyond 100 megaparsec. But within that, the conclusion of these authors was that, for now at least, there's no significant evidence for anisotropy in the local redshift gradient from the data sets they analyzed anyway, which include the supernovae. Beyond that, is it going to become isotropic and homogeneous? It's not that straightforward to tell.
Okay, thank you. Yannick, please go ahead.
Yes, so I have a follow-up question, because I'm thinking about this, what you said, and I would like to confirm if the viability of this simple interpolating function, is it actually confirmed for dwarf galaxies?
Well, first of all, you mean in dwarf galaxies are generally at such low accelerations that you're not sensitive to the interpolating function. You're only sensitive to the deep MOND limit.
Okay.
And therefore, the details of how you transition between the deep MOND limit and the Newtonian limit are not relevant. Now, if you're asking, does MOND itself, in other words, the deep MOND limit, work well in dwarf galaxies, at least with the isolated field dwarfs in the local group, it is known to work pretty well. There was a nice study by McGaw on 2021, which was I think this one, where they found that that MOND works pretty well there, but by MOND in that case, I just mean the deep MOND limit, because accelerations are too low. So to answer your question, you can't really probe the details of the transition function in dwarf galaxies, but you can hope to test MOND. You can hope to test the deep MOND limit, and that does seem to work.
Okay, because I'm curious about dwarf galaxies, not just normal and large galaxies of many kiloparsecs.
Yeah, but in dwarf galaxies, the interpolating function doesn't really matter. It's just the deep MOND limit.
Okay.
And that's kind of fundamental to MOND. So the predictions for MOND in dwarf galaxies are essentially independent of how you think there's a transition between the deep MOND and Newtonian limits.
Okay.
But it does depend on A0, of course.
Yes.
Yeah.
Okay.
Thank you, Pavel.
Okay, great. Thank you very much.
I have a question. Yeah, it's sort of, well, going back to your talk, Indranil, and so it's again a question of dwarf galaxies.
Yes.
Like Yannick is asking. The question is, you had this the isophotes of, I think it was it Carina, where you had a tidal tail, no? Where it was asymmetrical, if I remember correctly. Yes,
yeah,
exactly.
Assuming so that this is a tidal tail.
On the right is, on the right there are many more stars than on the left. Do you or Elena by any chance would know which direction the satellite is actually moving in this frame? Is it to the right or to the left or up or down?
I don't know about that. I mean, that's some. Do you know? I mean, I don't know if Elena is attending in the first place. Yeah, she is. But I don't know if you know. But that's an interesting question. I'm pretty sure it is reasonably well known, though, because
exactly. So in MOND we do expect the tail, the leading tail, to have more tidal stars, extra tidal stars than the trailing tail. So it's fairly.
Guillaume was saying that you need to be careful with that. That's true for orbits which are close to circular. With more eccentric orbits, one needs to be a bit more careful with that prediction.
Exactly. One has to be more careful there. Yeah.
Although I think it's safe here. Here, I'm just saying, in general, you need to be careful. Not for Carina, though, because for Carina, the eccentricity is very, very small. So it's very clear which direction it's moving in, and it's very clear that.
So Elena, if you're listening, could you maybe look at that, because this could be a highly significant effect. in Newton, we expect a higher degree of symmetry, especially for an
Well, hang
heliocircular
on.
orbit.
In Newton, there shouldn't be tidal tails.
Well, exactly. Apart from that problem, yeah. And then I had another question. You showed so you had the numerical simulation. I think Suf and Wu did those, no? Suf and Wu and Hefei, of the satellite galaxies as they're orbiting, the n-body models. Could you please show those graphs again?
Which ones do you mean? These ones?
The ones where you had the numerical, where you had these exactly. So one can see how the satellites expand. Now I think it's the lower right plot.
Yes. Yes.
So the half-mass radius expands, so like the green dotted line.
Yes.
Towards the end, they all basically expand if they're fairly eccentric orbits. And this fairly mild expansion before they get disrupted, if you now look at the a graph you showed for the Fornax cluster, where you had the size of the dwarf versus distance from the center of the cluster, where you have
we didn't directly show we showed the surface brightness essentially. Yes.
No. Yeah, this one. No. So this is basically the equivalent plot, and you can see an equivalent expansion, right? So to the left, the data tend to go up before one comes to the red line, which is the disruption line.
There has been a paper arguing that, yes.
Yeah, so if these numerical models by Xuf and Wu actually, if one would overplot them here, whether they would show a similar trend, it looks quite similar, right?
Oh, you mean they tend to go up a little bit? Yeah, it does seem that way.
Yeah, and I think that's a fairly direct consequence of the external field effect, because as the dwarf comes in, it loses its phantom dark matter and it puffs up.
I think you're correct, Pavel, but there are some more obvious consequences of the external field effect on this plot. Number one being the lack of dwarfs in this region, and number two, the much higher proportion of disturbed dwarfs very close to the red line here.
Yeah, sure. So those are the primary arguments, but as a
but you're right. There is a study that argues. Yeah, there is a study that argues exactly along those lines.
So we have a direct MOND prediction, which requires, because of the external field effect, these to puff up as in the inner parts, and that's what we see here. Yeah. At least qualitatively. The question is whether
there was a paper which argued along those lines that the dwarfs towards the cluster center were in general larger than similar mass dwarfs further away, and they attributed this to cluster tides. I don't think they did the extra step of working out, well, hang on, should cluster tides even be important in lambda CDM?
You don't expect, so if there is even fuzzy dark matter, you don't expect this effect, because you'd have to lose the dark matter before they puff up.
Well, in fuzzy dark matter, as I say, it depends on, well, in general, it depends on the amount of dark matter within the optical extent of the dwarf. Simply stripping dark matter beyond the optical extent of the dwarf will not do anything because of the shell theorem.
Yes, exactly.
But if you have very little dark matter to begin with, within the baryonic or the optical extent, that would work, I think. But I don't know if the fuzzy dark matter can deliver that, of course. And if it can deliver it, whether it would then run into problems elsewhere, I don't know about that.
Okay, thanks.
Sure.
Any more questions, please?
I have a question.
Hi, Roger, go ahead. It's good to see you.
Yes, very nice talk. I just want to know, in the scheme I'm interested in, there is dark matter, but it has a half-life of something like 10 to the 11 years.
Okay.
It decays into gravitational waves.
But what kind of dark matter is it?
Sorry?
What kind of dark matter is it? Is it like very massive particles, or?
Yes, it would be very massive. Yes, extremely massive, about Planck mass particles.
Okay.
And it would decay within about 10 to the 11 years half-life. Would that affect your considerations?
Not really, because I mean, first of all, 10 to the 11 years is much longer than a Hubble time. So the dark matter would not have appreciably decayed. But more importantly, we were essentially just I mean, many of the calculations we've done here of the tidal susceptibilities, sorry, where did it go? Yeah, where we calculated the tidal susceptibilities here, we'd replace the calculations from some lambda CDM based model with a model where you simply assume that that distribution of dark matter, the dark matter content, has to be the same as local group isolated dwarfs in the local group. So even if the dark matter were to decay over time, it wouldn't affect the fact that there shouldn't be any material difference between isolated dwarfs in the local group and dwarfs in the Fornax cluster. Like the dark matter content in the two cases should be the same. So I don't think a very gradual decay of dark matter on 100 billion year timescales would affect that result at all. It would affect the results we showed based on TNG50, but yeah, I don't think it'll affect. Basically, our results are a strong argument against massive cold dark matter particles of the kind you were mentioning.
Okay, thank you.
Roger, since you're here, I'm very curious to ask you, where do you stand on Milgrom's MOND and the subsequent modification of general relativity that it would entail? What are your thoughts?
Well, I've never really studied it in any detail, so I don't know. But if it's trying to replace dark matter, then I don't like it.
Why do you say that, Roger?
Well, in the scheme that I'm interested in, there has to be dark matter. It has to be a prominent part of the universe, a dominant part of the universe.
But does it have to be high mass, as you were suggesting?
It should be high mass, yes.
Okay.
I don't know how much of this is needed in the theory, but that's what it looks like, yes. A mass of about a Planck mass and a lifetime of something like 10 to the 11 years.
Okay.
But it would be a dominant part of the universe as a lambda CDM, yes.
Well, one difficulty for me, Roger, always has been with regard to assuming dark matter in galactic dynamics is this critical acceleration scale, the so-called A0. Why should dark matter have an acceleration scale beyond which the rotation curve becomes flat? That's more indicative of a modification of a law of gravity rather than, I've never understood where dark matter would give me a critical acceleration scale, and that too of the order of the cosmic acceleration.
I'm sorry, I'm not aware with.
But you've heard, Roger, of this radial acceleration relation, right? So this is the tightest extragalactic scaling relation there is. There's a very tight relation between the observed gravity that you get from the rotation curves, the centripetal v²/r acceleration, and the predicted gravity from the baryons alone, assuming Newtonian gravity, that is. And there is this
radial acceleration relation.
Yeah,
exactly.
Exactly. It's known in the literature as the radial acceleration relation, or RAR. And you can see it's extremely tight. I think it's supposed to have about 0.05 dex scatter or something. Well, 0.034 dex, I think, was the latest estimate from Harry Desmond. So yeah, it's an extremely tight relation. And of course, it defines a characteristic acceleration scale because the points follow a slope of half on log-log axis here, and they follow a slope of 1 further up, where the g-obs and gn becomes proportional, equal even in the solar system regime. So there's like a crossover point.
Yeah, to put it more simply, Roger, whenever the observed acceleration of stars in galaxies goes below a critical value of around 10 to the minus 10 meters per second square, the rotation curve begins to depart from the Newtonian prediction if there was only ordinary matter.
Yeah.
Okay. The scheme I'm talking about would certainly not differ that much from lambda CDM.
Okay. Thank you. Michael?
Yes, I was just going to say there's one other aspect of MOND which I would imagine that Roger would not feel comfortable with at all, and that is it implies having to give up the strong equivalence principle.
Oh yes, no, I wouldn't like that.
No, exactly. And which in fact brings my question: is there any weakened version of the equivalence principle that you could, theoretically recover in the Mondian framework, Indranil?
I mean,
it's sorry.
It still satisfies the weak equivalence principle.
Yes.
Oh, it does. Okay, I wasn't clear.
Yes,
okay.
yes.
Yeah.
But it is interesting. I mean, how weak? Can you say something more about that?
Satisfies the weak.
No, not in the sense of.
Where are you drawing the distinction between the weak and strong equivalence principles?
Yes, I mean, it satisfies the weak equivalence principle, as in test particles of different masses would accelerate at the same rate.
Yeah.
But yeah, so that's what I mean by the weak equivalence principle.
Okay, fine. That's good enough.
Yeah. But I mean, when you say you simply don't like the violation of the strong equivalence principle, I mean, why is that? Is there, because as far as I know, this hasn't really been tested in any great detail whether the strong equivalence principle would be valid.
We want GR. GR depends on.
GR predicts it would be valid. Yes, sure.
Yeah. One possibility I think we should allow, the GR is intact. GR is not modified on classical scales, but at low accelerations, a different force begins to dominate over general relativistic effects at low accelerations. That would not contaminate GR in any way. It just shows that there is something more about nature which we don't yet know and which is showing up as flat galaxy rotation curves.
Yeah, but remember, it shows up as anomalous lensing as well. So it would need to be a new force, but it also would need to essentially create new additional space-time curvature. It couldn't simply affect the dynamics.
I agree. It would be a force whose energy momentum contributes to curvature. That is true.
Yeah, that's what I mean. Yeah.
But it is causing departure from geodesic motion. Simply because it is dominant, not because general relativity is modified. There are two competing forces.
Yes, I think I understand. So it contributes extra energy momentum density, and that perhaps leads to the anomalous deflection of light by galaxies.
Yes. Yeah. Yannick is asking. Yes, Michael, Yannick is asking if we'll be uploading the recording of Indranil's talk.
I was just about to answer him, and the question is yes, it certainly will.
Great, thank you very much.
More questions, please. Pavel, go ahead, please.
Yeah, I can maybe, since I think we have about 10 more minutes, right?
We do.
Yes, so I just wanted to come back to this issue of isotropy, which was raised earlier, and then we went to the interpolating function. So there's an important effect which I think many people are not really aware of, apart from this KBC void, which already is a big problem and breaks isotropy on the scale of nearly a gigaparsec. But we all know that the star formation rate density peaks at about a redshift of 2, right? So that's the general statement we read about, and which is used also in all interpretation of observations. The problem with that is that if we reconstruct the star formation rate density in a cosmological context from the local 1,000 galaxies, which are around us in a region of about 11 megaparsec, which are fairly well studied. So we know their star formation rate history simply because the present day star formation rate is basically the same as the average star formation rate, which means the star formation rates of these galaxies are basically flat. They're not changing over the Hubble time. And so if we then calculate the star formation rate density within this volume and go back in time, we do not see this maximum at a redshift of 2. It's not there. And so if we now assume that the local galaxies, the 1,000 galaxies around us, are normal, like we assume the stars near the sun representative of the stars we see at the edge of the universe because the physics is the same, then we have to come to the conclusion that this maximum of the star formation rate density at a redshift of 2 is not a maximum of the star formation rate density, but it's an overdensity of matter. But it's a gigantic overdensity. So it's an overdensity by a factor of 100, and we see that at the redshift of 2, which means at a time when it was when the universe was still young. So we are seeing very strong evidence for a highly anisotropic universe. And we are in a very, very quiet region of the universe where we are within the KBC void, and that KBC void is part of a much, much larger underdensity and at redshift around 2, and so co-moving, I think co-moving volume about 5 gigaparsec distance, the matter density is something like a factor of 100, if not more, bigger than what we see locally. So this indicates strongly that the universe is highly anisotropic, which of course is radically, completely incompatible with the cosmological principle in as much as it's supposed to be, that the universe is supposed to be isotropic and homogeneous. Of course, the cosmological principle in the sense that the laws of physics are the same everywhere is not touched. That is still valid. It's just that the initial conditions were very different to what we thought they were, leading to a much more structured universe. I think that's what the evidence is showing us. And in this sense, how we interpret the micro CMB anisotropies and dipole directions then has to be reinterpreted, because we might be, depending on which sample of volume we are sampling, so which region of volume we are sampling, we're seeing matter flows which might be nearly which would not necessarily be aligning, right? And so then one would, depending on where I look, I would see a different type of overall, like a background, a motion relative to a background. The question is, the background itself is probably moving because everything breaks down. So the CMB would have to be reinterpreted, as I was indicating before. And so I think we are looking at a really radically different cosmological model than currently understood.
Well, one thing, Pavel, thank you. Thank you for your comment. We still have to take into account the success of Big Bang nucleosynthesis and the ability to produce that much helium in the early universe. So I would have been inclined to believe that yes, just after the Big Bang, it begins as homogeneous and isotropic, but once structure formation begins, it's not perturbative, it's extremely disruptive. It destroys the background so-called homogeneous isotropic universe, even on the largest scales. Does that look plausible to you? Because how would I solve the Big Bang nucleosynthesis?
Well, it can be solved. I mean, the background of this is what, given all this, what I was just saying, of course, with some people I've been looking at, especially with Eda Georgo, who's now a postdoc in Nanjing, I've been looking at how to maybe understand these issues, and they seem to be understandable within what we call the Bohemian model of cosmology, which is a very different type of model which has ever been discussed. It's not published yet. But that seems to be able to account for that. So we are doing cosmological structure formation simulations in that model. It is purely GR based, and these inhomogeneities do build up, and the primordial nucleosynthesis is different in that model, but it would be consistent with what we observe because of certain processes which are not part of the lambda CDM model. So these things can be, I think, understood, but there's much work ahead, and I'm currently speaking about insights and knowledge which has not been published yet. So we have to be, at least I have to be very patient to wait until we manage to get this published.
But can you just give us the name of the model again? I didn't quite catch it.
What is a Bohemian?
Bohemian model of cosmology. Yes. Bohemian model of cosmology, because I was looking for a name and I thought it is so crazy that it's called Bohemian, although
see.
actually it is much, much less crazy than lambda CDM because it doesn't have any of these ingredients. It doesn't have dark matter, no dark energy, no inflation, no new fields. So it's actually, in a sense, a carefree model, but it seems to work. So we've got it in a computer. We see galaxies forming, galaxies form a redshift of 20. That's this Ingo Thies is doing these simulations, and Nick Samaras too. It builds up major anisotropies. So, I mean, inhomogeneities as well.
What were the initial conditions at the beginning? Was there a hot beginning?
Well, the thing is that since this is not published, I have the agreement with Edagioru that we don't speak about the details until it's published. And
Okay.
I did not actually want to mention it here, but I drifted into that because of the inhomogeneities and some dimension in thesis. So the initial conditions might be very different to what people think now.
Okay.
So hopefully we'll find out more about that in due course.
Yes.
I mean, so in any case, about the inhomogeneity, I think to bring it back to a common denominator, if you want to explain anything about sort of inhomogeneity and anisotropy, then you have to be able to explain in any cosmology the KBC void. And as far as I'm concerned, like everybody knows what the Hubble tension is, for example. For some reason, very few people are really even aware of the existence of this KBC void, let alone having this as a constraining factor on anything. And I'm very surprised by this, really.
Okay, thank you. Yeah, that's a good point. But are we still in at least basic agreement that the universe is expanding? That still survives. Yeah.
It might also be cyclic, you know.
Yeah, that Roger likes, right?
But at the current phase, it's expanding. I think that's reasonably clear.
Okay, anything more? We still have 5 minutes. Okay, so the schedule with Pavel will talk on October 17. And then we have a gap, Abhay Ashtekar, November 28. As of now, that's the schedule for this year. I have not been able to find enough speakers. I was looking for someone to talk on the little red dots. I asked Priyamada Natarajan, but she said next year, not this year. Michael, we should cover the little red dots. It's a very interesting development.
I agree, it is extremely. But we obviously want to wait until somebody who's qualified to present on it has it feels they're ready to speak. But that does leave us with at least three or even 4 slots.
Yeah, we have 3.
In November, you were saying, is that right?
November 28th, Abhay will talk.
That's Abhay. Abhay is going to be talking about.
Then we have 2
so basically, right. So basically, pretty much all of November is otherwise
2
free.
November and 1 December slots are free. Yes.
Right.
Yeah. I was also hoping, Michael, that there'll be some talks on 3 fermion generations, but Cole and Niels Gresnik want more time.
Yes.
Then get ready to talk about it.
Well, if there's anybody out there who has any recent developments in their own program,
also,
in their own work.
Michael, Roger had very kindly agreed that he will give a talk on my life as a scientist. Whenever you are ready, Roger.
Yes.
Did I agree to that? I forget.
Yeah. Well, we would love to hear you, because you said you have not in the past given a generic talk like that. We would love to know how your thought systems developed from your... You were with Paul Dirac, right? He did your quantum mechanics course.
I went to his lectures, yes.
Yeah. Did you ever meet Albert Einstein?
No, I was too late for that, I'm afraid. But Dennis Sharma did.
Yeah, he told me. I was Shyama's postdoc long ago.
My stepfather played played the piano to Einstein's violin. And he said the trouble with Einstein's playing was that he couldn't keep time.
Ah, and where was that? In Germany or England?
Sorry, that was in Princeton, I guess.
In Princeton.
Okay.
In Princeton.
Yes.
Mm-hmm.
I don't know. I think it was Princeton, yes.
I think not many people are around now who have met Einstein.
No.
Sadly. John Stachel, of course, was one, but he sadly left us earlier this year. So, but still, very interesting. I mean, I know you've got an awful lot on your plate at the moment, Roger. So we're not sort of pushing you, but it would be wonderful to hear that talk when you feel up for it.
Okay, well, not too soon. I think.
No, don't worry. We won't.
Yeah,
We've got lots of other things to do in the meantime.
Early next year, maybe we could open with your talk for the next year's session. Yeah.
I might be able to give a talk in November, perhaps, or early
In
December.
Indranil, we will not repeat speakers so often.
Oh,
You
okay.
have you have given 3 OSMU talks, but now I think we will have you back next year.
Do we have anybody else there who has?
I could. Well, I was thinking of a completely different topic, but I could ask one of the other members on my team to give that instead. We have much more accurate results on the age of the universe. So this is a general constraint of cosmological models.
Yeah, this would be
I also
interesting.
am looking for more talks on the dipole anomaly. Subir gave a talk, but I was very impressed that Reviews of Modern Physics published their colloquium on the dipole anomaly. But you are saying, Indranil, it's still under debate.
Yeah, it's still definitely under debate. I mean, you have to be careful with, especially when combining surveys. Like I think the number counts in one survey was scaled by some arbitrary factor relative to those in the other survey. But you have to be careful with accounting for uncertainty in that and doing a proper Bayesian analysis to infer the strength of the dipole jointly with the other parameters, such as this relative calibration and other things. But and also, of course, the source evolution effects. The fact that the co-moving number density of quasars changes with redshift.
Okay, thank you. Okay, so we'll see you at Pavel's talk. Sorry, Nick Samaras. Okay, what could we cover with that, Pavel?
Well, the power spectrum, say what he did on that.
Okay, great. Yeah, I will.
Oh yeah, that would be cosmology as well. Yeah.
I will definitely contact him. Thank you.
It would be very nice to have these cosmological talks for sure, but I was hoping we could find one space for one more general foundational talk, querying the, to the kind of level of foundational consequence that we had, for instance, with some of the ideas that Igor presented a few months ago, or indeed the very first talk Roger ever gave on the split octonians. Don't know if there's anybody who feels.
Have you thought about Alexia Lopez and her circles of galaxies?
Oh
no,
yeah,
that would be very interesting to have as well.
Yeah, definitely.
I was thinking something more on the mathematical side, but that
these are observational,
very interesting.
Yeah.
Well, so what's George saying? Quantum computing, yeah, definitely. That's a good point. Yeah, definitely, yes. Thanks for the suggestions. I try to act on them. Okay, then. So see you on October 17th. Thanks for coming today.
Thanks to everybody for coming today. It's been a very good lineup and a very good discussion. Thanks. Very good to have you with us, Roger, as always. And thank you, Indranil, for a really very, very... the phenomenology is immensely multi-layered and intricate, but fascinating in the way you've told the exposition of it is...
And thanks for the wonderful discussion we had.
Yes, and the discussion has been very good all around. Yes, I think well up to the OSMU standard. So thank you again to everybody. We'll see you again on the 17th of October.
Bye-bye. Logging
Take
out.
care.
Bye.
Take care, everybody. See you again soon.